Ladies and gentlemen, please welcome Technology Manager for Development Tools, Godfrey DeGiorgi.
Good morning. It's good to see that on a Friday morning we get as many of you here for an early morning session. How's the show been going for you? Yeah? Good. Great. We've talked to you over the course of the week about various technologies in our frameworks and our applications. We've seen Jaguar and all the new things we're doing there. Today we're going to be focusing on a lot more of the tools in terms of their detail aspects and how to use them and stuff like that. So for the first session today, we're going to talk about developing for performance. And to do that, I want to introduce Joe Sokol, the manager of the Core OS Performance Group. On the podium.
Hi, good morning. Hope everyone had a fun time at the Beer Bash last night. Maybe be a little bit awake this morning for this. Anyway, I am Joe Sokol, and man, that's very sensitive. Okay, so today we're going to actually talk a little bit about performance philosophy as opposed to the actual APIs and things that you might use to make your applications go. So the philosophy that we've kind of chosen to follow here is that, improving system performance is like a diet, right? It's a never-ending battle. Once you start down this road, you've just got to kind of stay with the fight. And just like a diet, it's a lot easier to do, if you're participating in a group, as opposed to doing it individually. So today, what I'm going to be asking you to do throughout the session, basically, is to go on a diet, right? A diet in terms of the system resources that you're using. To win this battle, we need to look at using our system resources efficiently. Okay. Both when the app is quiescent and when it's actively running and doing something. Now, quiescent does not necessarily mean that it's in the background. That app could be in the foreground. If the user's not interacting with it, it has no work to do. It should do just that. It should take no system resources. Excuse me. When the app is active, we'd like you to use the system resources as efficiently as possible to implement whatever work that you have to do. So, you also need to pay attention. Basically, what we're asking you to do is pay attention to the fundamentals. Okay, so these are things that everyone has learned as an engineer through the years, but sometimes we forget. And what we want to do is really focus on why this is important to system performance. There are no magic APIs. I cannot give you an API that basically puts you on a slim, fast diet and makes your application more efficient, right? It's up to you guys to actually go and take a look at what's going on and make changes in how you're utilizing these resources. Okay, so basically we're going to go through this in 3 stages today. I'm going to do a brief description of the difference between performance and efficiency. And why you care about both of these concepts. We're going to talk about the fundamental elements of system performance. So these are the 3 things when I'm referring to system resources. These are basically the 3 things that we're talking about. Use of the CPU, use of memory, and use of file system. And at the end, we're going to go through some processes and some lists of tools on how to evaluate your use of these system resources. Okay, so performance and efficiency. They're not synonymous. People get these confused all the time. Performance is a result of efficiency. So the more efficient you make your application, the better it's going to perform in a variety of environments, not just in a kind of standalone test bed that you might be looking at. And performance does not guarantee efficiency. So you may go and really work hard to make your app perform and meet certain criteria that your customers are asking for, but that does not necessarily guarantee that it's doing it in an efficient way. And in fact, often that's what happens. You set a performance goal, you reach that goal, and then you stop. you may be consuming 100% or 90% of the system available resources at that point, but you've met your performance goal. Okay. The processes for improving both are very similar, and again, we will address that in the kind of third portion of this talk. And also, we're going to talk at least why you should care about each of these points as we go. So what is performance? It's the speed at which operations complete, right? It's something that is measurable. It's something that is perceived by the user, which is why you care, because it's also something that the user is going to call in and complain about, right, if it doesn't meet his requirements. Some common performance metrics that are used to measure this, to measure how well you're doing, would be things like throughput, so bytes per second, so maybe how fast you can move that file across the network. Operations per second, so that would be maybe like the number of frames per second that you could draw on the screen for maybe like a game, something like that. And of course, latency, which is pretty much what the user always sees, right? It's the response time. So he sees all of these things as a request that then takes some amount of time to actually complete. And that's really what interests him. So how long does he have to sit in front of the screen there and wait for that operation to complete? So what is efficiency? Okay, so efficiency in this context is really the cost to complete an operation. So for any one of those given operations that your app is making many thousands of, what was the cost in system resources? It minimizes the use of system resources. So if you have an efficient algorithm, it tends to minimize the use of system resources. Efficiency metrics that we use to measure how well we're doing would be CPU usage, so which would be a percentage of the CPU used over some period of time. So that might be over a short period of time or a longer period of time. There may be peaks in there, but generally we look at it as an average. The memory footprint, which is probably the most critical of the three to look at, because that kind of dictates whether or not things are really going to operate efficiently, and I/O frequency. So how frequently are you going to the disk, and for what size operations? Okay, so this all kind of rolls up into system performance. System performance, when we talk about that, what we're really talking about, it's a result of all the individual apps and OS efficiencies, right? So when you roll that all together and you take a look at a system and it's got 20 applications running on it, it has a bunch of stuff that the system is also doing, that really dictates how well the system is, or the efficiencies of what you're doing there really dictate what the system is going to perform like. It's heavily affected by the working set size. So if your working set size exceeds the amount of physical memory you have, the system performance just tanks. It's not a slow drop-off. It just becomes, pretty much unusable. Why is this important to you? Because the system performance affects the user's perception of any individual application performance. So you guys can work really hard to make your app perform really well, but if you've tested that in isolation and you haven't mixed it in with other applications to see how they affect it and what the system is going to do to it, when the user actually uses it, they may see a very different thing, right? Your testers are telling you, hey, we meet all of the performance goals that we set. Everything looks cool. All of your customers are telling you, hey, this thing just doesn't rock, right? It's not performing the way you claim it's going to perform. So how do we go about improving this? Because that's really the nut here. All right, we focus on the fundamentals. Okay, there are three fundamentals that really control how well the system is going to perform and how efficient you're at. It's your use of the CPU, it's how much memory you're actually tying up in a working set, and it's how much file system I/O that you're initiating. When you look at it from that perspective, that every system performance problem that I look at, right, it always boils down to one of these three things. All right, in looking at the CPU, there are two models that are commonly used. And I know that we've been driving this point home, I think, throughout the conference. I was at the Carbon event session, and we're asking you to be event-driven. This is really a good way to control your appetite for the CPU. The important thing here is that only real work is done. So when you get an event, you respond to the event, right? You do the work that's necessary, you do it in an efficient way, and then you go back to sleep. The app can become totally idle, which is a really good thing. We're going to talk about a couple of implications of that here in a second. The other way to go is more of a polling model. And the thing that's really bad about this is that often, in fact, the majority of the time when you poll, there's actually no real work for you to do. You run around your polling loop looking for things to do, and the majority of the time, there's no real work to do. So it's a pretty inefficient use of the resource. Now, the other thing that happens with the CPU is every time you use it, right, you're causing memory and possibly the disk to be accessed. So it's a VM system. You don't know whether or not that piece of memory you're touching is really physically present or not, or it's going to have to come in off the disk. So why event-driven? So really, fundamentally, what's really good about this? In terms of the fundamentals, anyway, it minimizes the working set. If you're only responding to events and only doing the work that's absolutely necessary, you're going to touch a lot less pages. Touching less pages means that there's less paging going on in the system. It just means the system is going to feel that much more responsive. Another point that you might not think about is the ability of the system to aggressively manage its power. In macOS 10, we do all of our power management basically in the idle thread. So the system has to go idle before we can start to make use of any of the little hardware tricks for napping or dozing the processor, or possibly doing frequency shifting if that processor is capable of doing that or it needs to be done. And the more aggressively we can manage power, the longer a battery lasts in a portable. And the fan just comes on less often, too, in like your TI. So, that's a good thing, too. People complain about that. They don't realize there's a fan in there until, the system has been banging around for a while. And there are more CPU cycles available to do real work. So if you're not using the CPU to just go poll for things to do, that leaves CPU cycles available for other applications. And why not to poll? So it's just the converse, right? When you're polling, you're basically keeping a larger working set heated, and that means there's going to be more contention for memory. When it's a single app doing this, it's easy to say, it doesn't really matter that I'm going around this loop and making a few API calls and touching a little bit of memory. What can that hurt? But when you think about it in the context of there are 20 applications running or 30 applications running on the system that people have started up, forgotten about, and they're sitting in the background, it starts to add up, and it starts to make for quite a bit of contention for memory. More contention for memory, more paging. If the system is paging, it's a sluggish system. It's just not going to perform very well. And then back to our power management point. The system, if we kind of take this to an extreme, the system may never become idle, or it may be idle for only short periods of time, not enough for us to really do anything with the power management, so the power management may be compromised, and the battery life shrinks, the fan is on all the time, people are unhappy about that. But that's a part of system performance that people pay attention to, right? How long that battery lasts. And it's an inefficient use of system resources. You're going to be using the CPU, touching memory, possibly causing pages to come in off the disk to find out that you don't have anything to do. There isn't really anything more inefficient than that. I mean, that's just about as bad as it gets. All right, so touching memory. So we've got this CPU. He's executing some instructions. What happens? All right, so if everything is like really operating nice and tight in your cache, you're just sitting in this L1 cache, and you're just banging away at it. The TLB there is the translation look-aside buffer for doing the virtual to physical address translations at the CPU level. That's a good place to be, right? As memory use expands, then you get into maybe the L2 cache, the L3 cache. Now you're down to memory. You can see we've color-coded this so you can see that as we move further down the chain here, things get slower and slower. So at this point, if we're actually executing out of memory, so if our working set, if the set of memory that we're touching has exceeded those first level caches, if we're executing out of memory, we're running 10 times slower than the L1. I mean, and it's actually probably a little worse than that on a faster processor. If we're actually hitting the disk, right, to go get data or to go get code that has to be executed in that polling loop, you're now running 10,000 times slower than the L1. So you can see why you want to stay out of that case. The other thing to note is that if you just touch 1 byte of memory, it has a lot bigger impact than you think. Caches are organized around 32-byte cache lines, right? So to get that 1 byte in, you're evicting, another cache line all through the L1, L2, and L3. The TLB table is built around pages, right? So if you have to address a byte in a virtual page that it currently doesn't have an entry for, it's going to evict an entry in order to make that translation. And that basically represents a 4K set of addresses that are being tossed, right, in terms of translation. Memory, we allocate everything in 4K pages. So the minimal size physical page of memory that you're going to get when you touch a byte is going to be 4K. So that means, again, your byte basically is causing 4K worth of data to be evicted. And the disk is managed the same way in terms of 4K pages to back that. But again, up around the processor, if you can keep your memory appetite small and you can, keep everything in the caches or worst case in the memory, the system performs a lot better. Once it goes to the disk, things get bad. All right, so now let's move on to memory. All right, so again, in terms of the fundamental thing that we're looking at here, it's really the working set. This is really the thing that controls system performance. And basically, a working set are the pages that are being actively touched by the application. So these would be, could be in RAM, hopefully they're in RAM, but could be out on the disk also. And let me tell you, when you're working set, so if you have a set of pages, a set of memory that you have to go pounding through in order to complete an operation, and you can't get it all to fit into your physical RAM, right, that's a bad place to be. You have to be aware of that fact that if you're banging on memory, it may actually be coming in off of the disk. What does the working set consist of in this case? Well, it'd be all of your heap or heaps and any code that you're executing. Every API that you use increases the size of your working set, right? Sometimes it has long-term effects. So sometimes it's short-term, like you're heating up stack pages, running some code. Other times, though, it's actually leaving memory allocations behind, right? So like window buffers, which can be quite large. So again, be aware of the fact that each API you use has a cost. Leaks increase size via heap fragmentation. So interestingly, as we've moved along in the OS development and the OS has become more stable, applications have become more stable, we've implemented things like sleep capabilities for the system. People are not rebooting their systems nearly as often as they used to. People are not quitting their apps either. So what ends up happening is you now have applications that are very long-lived. They may be actually running for weeks at a time before they're either quit or the system is rebooted. Time is your enemy when you have a leak, right? It's just, even if the leak is slow, eventually it will start to build up. And what will happen is, depending upon your usage patterns of how you're allocating memory and how those leaks are showing up, it may actually be increasing the size of your working set. So if the leak doesn't all happen at once, right, and just get paged out, right, never to be touched again, that's not so bad. But if it's mixed in with your other allocations, longer-term allocations, then you're expanding, you're basically diluting the mapping between your allocations and the physical pages to back it, right? So instead of physical pages containing 70 or 80% of good, useful data, with leaks mixed in, maybe they're down to 20 or 30%. So again, be aware of the fact and really take a look at your application. And even if it's a slow leak, go after it and get rid of it. Another thing that you can assume is that long-term caches are always paged out. So if you're creating a cache and it's building up over time, when you go back to access it, be very careful in how you do this. Try to avoid walking through the whole cache. If you can just do like hash lookups into it, that's fine. But when you're doing maintenance, be aware that when you go running through the whole cache, most likely, really high degree of probability, it's been paged out, which means you're going to page it all back in to do some little bit of maintenance. You need to really be aware of that and make sure that if you do have to do it in a way that's efficient and that you're not doing it too frequently. Best performance when all the pages are in RAM. Again, can't stress that enough. The system performs a lot better if it's not paging. So how does your memory appetite and the VM, how do they interact? Well, here's the problem. Typically 40% of the pages of the system are dirty. So these are valid pages that some application wants to keep a hold on, but they're dirty. They've been written to, which means that we're going to have to write those pages to disk whenever unused pages are not available. New memory is accessed. So if you go and allocate a new big chunk of memory and then go and access it, the very first time you access it, we're going to have to provide you some physical pages. Well, those physical pages have to come from someplace. And the system is going to go through, and there's an LRU to keep track of working sets and all that. But basically, when the system is running, kind of saturated, we're going to have to page pages out. So when you initiate file I/O, that's also going to possibly trigger this. And of course, when you're paging, this is the worst case. If you're paging pages back in that you need, and we're having to page pages out in order to make room for them, right? So you're getting a dual kind of I/O going on there that you don't want to have happen. Clean pages in the system are just stolen, but again, 40% of the time when we go to steal a page, we're going to have to write it out when the system is kind of in a steady state, fully used or utilized in terms of memory. All right, so let's talk a little bit about working set impact. So here's a way to basically organize a cache that is probably fairly common, where you have a header attached to some data, and you just kind of allocate the whole thing, chain them together, and hopefully get some use out of the cache. But the thing to remember here is that each time you touch any portion of that item, so this element, you're bringing the whole page in. So if you just need to run the list to update timestamps or do some other maintenance on it, and you're not actually you're not actively looking at the data at that point, you're still causing the whole page to be brought in. So if you had a cache with, say, 10,000 elements in it organized this way, and you chose to run through and do some maintenance on it, you're touching, basically 10,000 pages of memory. Unlikely that will be sitting in the cache or sitting in memory at this point. So here's another way to organize it that reduces that in the case where you're having to do these maintenance functions. You break out the headers into their own separate allocation, right? Point them off to the data. So at least in the case where you're having to go through the headers to do something with the timestamps or whatever, it minimizes the impact, on the working set. Now, with that said, there is still a downside to going this route that you have to be aware of, which is if you're allocating these things into your cache over time, so if there's a lot of temporal spacing between the allocations and between the insertions into the cache, you're not really going to help if you do each of these headers independently because, again, they'll spread out through your working set, and we'll end up with each one of those little headers being in its own page, right, but mixed in with other things, not with your data, and it won't have accomplished anything. So in this case, if you absolutely have to have a cache, when you break it into this kind of organization, make sure you cluster allocate those headers. So, ask the system for enough memory so that you can have 100 headers, right? And then you keep track of that and dole them out, right, as the cache grows. And when you run out, you ask the system for enough memory for another 100 headers. So at least you keep the headers compressed, right, in terms of the amount of physical memory that they're sitting on. So that's a lot better way to do that. Okay, so now we're done with memory. Moving on to file system I/O. All right, so sequential versus random file I/O. This is an interesting thing. Again, we've kind of come to expect that disks are fast. The kind of modern disks that we ship now are easily able to do, 40 megabytes per second sequential, a single disk. But that's going purely sequential, which we often don't do in the system. And in fact, when we're paging, we never do. When we're paging, we're doing much more random accesses on the disk. And disks really have not gotten any faster in the last 6, 7 years, 8 years. They really don't randomly seek much faster, and basically the throughput that you can get out of a disk that's purely random is only around 0.4 megabytes per second, so it's about 1% of the sequential throughput. It's about 100 IOs per second. That's really kind of pushing it. That's like a 7,200 RPM drive, right? Some of the slower drives in a portable that don't spin that fast because of power considerations, they're not going to even yield this. So that's just something to keep in mind when you're accessing files too, that sequential access patterns are a lot better than random access patterns. Now, larger IOs are more efficient up to a point. We really like you to not do 1-byte reads. That's not a very efficient way to get your data out of the file system cache. So larger IO requests are more efficient. But the thing to remember about this is that your IO buffer that you've created and that you're sucking data into, that basically consists of dirty pages after the IO is completed, or while the IO is completing. So a reasonable size is 128K. I mean, that's, it could be smaller, it could be a little bit larger. That's a pretty reasonable size that will pay back good dividends in terms of the efficiencies making the requests, but doesn't get too much in the way of the system in terms of a lot of dirty pages. Again, taking this kind of thought to an extreme, if you were to create an IO buffer that was, say, 32 megabytes in size, and you issue a single read of 32 megabytes to fill it, it's because you've got files that are gigabytes in size, and you think, well, Joe said, bigger is better when it comes to I/O, so let me go to 32 megabytes. Well, what would happen there potentially is that as the I/O is completing, because it doesn't all complete at once, right? Early pages are being filled with data. As the I/Os are completing, we're releasing those pages back to the system. By the time that you actually get control back, that your read is completed, if the system is busy doing other things, we may have paged those pages out for you, right? So your I/O buffer is now sitting out in the swap file. And when you come back to touch it, right, you're going to pay the cost of sucking it back in off the paging device again. So you'll actually end up with, doing at least 2 I/Os there, probably more, because we'll probably also be paging stuff out again to make room for it. So that's why I say, it's up to a point. You don't want to take this to an extreme. Another way to go would be to investigate doing some file mapping for reading large files. So in the Cocoa world, I know this is kind of the norm. In the Carbon world, this may not be something that you're used to doing, but it's something that you should investigate using the basic system primitives for actually mapping files and touching them in that way. The interesting thing about this, of course, is that you don't create any dirty pages. If you're just reading, the pages, are brought into the system, but they're not dirty. They can just be tossed if they need to be tossed in order to make room. We don't have to page them out. And if you go back and retouch the memory, we just go back to the backing file and retrieve it from there. There's no swapping involved at all. All right, file system metadata. Okay, so something, again, that people often forget is going on behind their back is that the file system itself has a lot of maintenance to do in order to keep the file system coherent. So whenever you're creating or deleting, writing files, directories, there's a lot of metadata that's going to be written, catalog data, directory entries, whatever. And that's not so bad. I mean, at least that comes along with the actual writes and stuff to the disk, your data. You did something, it needed to be committed to the disk. We have to commit that data plus maybe some of this metadata. But on the flip side, when you're enumerating directories or just reading files, even in the cases where those directories and files are cached in the file system cache, in 10, we're actually keeping track of the access times in those cases, and those access times are part of the metadata. Now, we don't write those out right away, but every 30 seconds, the update process is going to run. It's going to issue a sync on the system to try to sync out anything interesting to the disk, and it's going to go ahead and sweep all those up and sync them out to the disk. So if you're sitting there polling, looking for some work to do by enumerating a directory, looking for a file, say, waiting for a file to appear, basically what you're causing to happen is every 30 seconds we're going to write the disk. Okay, that's going to keep the disks from going to sleep. So that's not such a good thing. A better way to do that would be to stat the file or do a git cat info and look at its modification date, look at the directory's modification date to see whether it's changed or not. Because the stats, just retrieving the information about that directory, doesn't cause the access date to change. So in that case, you could sit there and keep accessing, looking to see whether anything new has come into the directory, but you're not having any impact on the file system in terms of IOs going to the disk. And then network file systems. So something to remember here is that in 10, we're doing a lot of work to try to hide the fact that particular volumes are out on the network or they're local. We're trying to give the illusion that it's just one big data store, right? And so you have to be aware as developers that your application may actually be living out on a server, or if it's not living on the server, maybe the preference files or your history files or your cache files that you're creating actually are ending up on a network server someplace, not on a local disk. So you need to take that into consideration. You need to probably you do, it's not probably, you need to test with that in mind. So when you're doing your final testing to see how things perform, make sure you do some testing with things targeted to networked file systems, not just off the local disk, because that's the way your customer is going to use it. And basically the thing to remember, network performance is unpredictable, right? So again, if you're designing something that is predicated on your ability to predict how long the I/O is going to take to complete, then you need to really make your customer aware then that he needs those files to live on a local disk, that he cannot have them sitting out on a network store someplace. And then the third point here is polling models tend to overwhelm networks. Again, when it's 1 or 2 or 3 machines that are doing it, it's not too bad. When it's 2,000, 3,000, 4,000 machines in a K-12 institute or higher ed institute or a larger corporation, the network administrators really dislike that, right? If you're sitting there constantly banging on the net, looking to see whether a file has come into existence or not, that's just not a very good thing to do. All right, so the big message here, the fundamentals are important. It's the most important thing that you can be looking at, right, is that your app does not run in isolation, right? Your app your app affects and is affected by other apps. That's basically what we're saying here, is that when you're testing, don't assume that just because you've reached a certain level of performance or efficiency that is adequate, right? Testing in isolation. You need to really look at it, with some other typical applications that your customers might be running when they're running your application. And app efficiency, this directly drives system performance. We can provide you very efficient APIs, which we really don't do yet, but we're working on it. But even if we did, if the app is intent on using a lot of memory, there's not a lot we can do about it. There's only so fast that we can move pages in and off of a disk, right? Most of our systems ship with one disk. There's contention for just normal file system mixed in with all the paging that's going on, really the only way to keep the system performance, adequate is to everyone, stay on this diet, right, and really control your appetite for memory. Minimizing the working set size. I mean, this is really the thing that we're driving, or I'm driving at today. I mean, this is the most critical element. And to reinforce this, so let's take a look at what's going on in terms of working sets. Say you've got, you've got a system working set which basically consists of like the finder, the dock, all of the little daemons and things that run behind our back to make the system work the way it does. Wired memory in the kernel. There's a whole bunch of stuff that just kind of sits there. Some other set of applications, and I threw in, IE and mail as some typical things that might be running on the system all the time. So stuff that you probably would never, you never really quit. It doesn't have to be our mail program, but any mail program. So say at this point, the sum of all the working sets, so the things that everyone, the working sets that the apps are keeping hot, either through their idle loops or through work that's being requested, or event processing, whatever, say that represents 80% of the physical memory that's available. At this point, this is really good. You've got 20% headroom here. The system is going to feel very snappy. You're going to be able to do things with the applications that you haven't been doing, and they're going to basically be able to happen without any page outs occurring. The user is going to be pretty happy in this case. But now let's say the user decides he wants to listen to some music, so he brings iTunes up. So now iTunes is put in the background, and he kind of forgets about it. And it's playing elevator music or whatever. It's just providing some entertainment for him. And say that again, this is not to scale, not to say that iTunes utilizes 15% of any physical memory footprint, but let's say that put that and maybe some other apps that were launched push this up to 95%. Well, at this point, as long as you don't sneeze, right, the system is still going to be fine. So basically, don't touch it, don't ask it to do anything that it isn't already doing, and it's probably going to be okay. But there's very little headroom here. At this point, almost anything that you do that you haven't been doing, so if you launch another application, if you print and you haven't printed, in a long time, almost anything major that you do is probably going to cause some paging to happen. But it's still not, it's not fatal. Basically, what will end up happening is there'll be a little blip, and then things will settle back down, and, okay, fine. It didn't feel quite as good as it could have, but it wasn't horrible. Dang it. All right. Now let's throw in, let's say, your app, for instance. And again, not to say that any one app is going to take this much space, but just for purposes of keeping this short. And we push the working set up to 125%. So the sum of all the working sets. So this is, every second, basically, you're trying to touch memory that represents 125% of your physical footprint. You are now in, like, no man's land. Your system is thrashing. You don't want to be here. Anything that you do, anything that you try to do is just going to be painfully slow. And there's not a whole lot we can do about it. I mean, if the memory's being touched, we have to shuffle it in and out. And we do our best, but we can only go so fast. All right, so how do we avoid that situation? We go on the system resource diet. Okay, so again, we've been talking about this. You need to minimize your working set, right? And a couple of good ways to do this. Lazy initialization, right? So when your app launches, don't initialize everything that it could possibly do and touch a bunch of memory. Wait until the user actually requests a particular service. I know a lot of apps have a lot of really cool features, but they're not all, they're not always used, and certainly they're not always used at once. Event-driven, again, we talked about that, and we've talked about that in other sessions, I'm sure. That will tend to really help control the working set. Don't optimize at the expense of efficiency. So again, if you look at it in isolation and you're trying to improve a particular aspect of performance in your application, and you choose to do this by, say, creating a very large cache because you say, hey, the disks are too slow, I don't want to deal with it, I'm going to pull all my data that I need, I'm going to slam it into a cache, and that's what I'm going to use. Well, your app may actually end up running slower, right? depending upon what the other needs of the system are, other applications that are running, you can't assume that you can have all the physical memory, right? There are other apps running, they need to share that. And what will happen is your cache will just ending up being paged in and out, and it'll be paged in and out at our discretion and the patterns that we choose, and that may end up making your app, just not run as well as it could. Caches are not necessarily evil, but they should be used, as a cache. If you're going to be accessing a particular cluster of data, over a very short period of time, sure, pull it in, keep it in the cache, but basically understand that it might be better for you to release it when you're done and then recreate it later when you need it again, as opposed to letting it go out, depending upon how long it takes you to create it. You have to monitor efficiency during development, right? This is not something that you can do after the fact, or it's not done easily after the fact. You want to watch your CPU usage, memory footprint, file system IOs. I'm going to talk about the tools here in a couple minutes, and how you would apply the tools to do this. But this is really critical. If you're not monitoring, you don't know where you're at. Don't test in isolation. So once you've decided that your app is performing okay, come up with some kind of a test scenario that includes a half a dozen or 7, 8 other applications that you think that your customer might have actively running on the system. And remember that, again, we're encouraging them to leave the apps running, right? I mean, that's what the dock is for. People launch applications. A week later, they're still sitting in the dock, right? They've forgotten that they even launched it. If that app is continuously polling, it's putting a load on the system, it's not doing anything for the user at that point, other than chewing up resources. All right, so here's a recipe. This is a basic recipe for improving efficiency. And they're really, there are probably different ways that you can cut this a little bit, but basically it all boils down to having some process that you can repeat and something that is measurable. So you want to set a goal, right? You don't want to just go into it thinking, well, I'll just start, making my code more efficient and we'll see where we, kind of get to. You want to set a goal. You want to look at how much memory you're using currently and say, let's see if I can cut that down by a third or cut that down by half, right? Set a very aggressive goal. Identify a metric that you can measure, right? And then measure it. Get yourself a baseline. Really understand what your app is doing at this point. Once you've done that, use the tools that we're going to talk about to analyze where that memory usage is coming from. So where in your application are you actually allocating all that heap space? And then apply, go through, analyze, apply the changes that will bring that usage down, and then iterate until the goal is met. It's not a one-step process. Often you're going to have to go through this 6, 7, 8 times in order to actually hit the goal that you've set for yourself. It's unlikely that you're going to catch it the very first time. Okay, improving performance. So it's the same recipe. So I'm asking you to improve efficiency. Your customers are asking you to improve performance, right, or specific performance aspects of your product. You can use the same recipe for doing this, right? You set a goal, select a metric which will be different than one for efficiency, right? Measure it, apply, and iterate. I mean, this will work, right? This works every time. Now, the thing to remember is you should be monitoring all those efficiency metrics while you're doing this, so that while you're improving your performance in one area, you don't want to become less efficient in terms of your fundamental usage. All right, so here's some tools that we can use to actually go after this stuff. So to look at what you're doing in terms of CPU usage, I've broken these things up into 2 categories, basically, the tools. There are tools for monitoring, which basically just give you an idea of where you stand, right? How much of these system resources that you're consuming. So a good one for CPU usage, an easy one to use, is top with either the -D or the -A option. The D option just gives you a snapshot, basically, a delta. So what happened in the last period, 1 second period, 5 second period, whatever period that you select. The -A option is kind of interesting because it basically it accumulates all of the data from the point that you launched top, and it gives you a snapshot then of what happened from that point through to the point where you decide to stop it. So it's really useful for kind of getting an idea of what impact you have on the system, like when you launch an app or you do a particular operation like maybe print or save a file. You could start with the -A option up right before you start the operation and then shut it down right as the operation finishes. And it'll kind of tell you, okay, for that period of time, this was my impact on the system. I used this percentage of the CPU. I did this many file IOs, that kind of thing. Now, for analysis, we have quite a bit. There's Sampler, which is a UI-driven, or sample, and hopefully you guys made it to the 9:05 session yesterday afternoon and saw some of this stuff being demoed. I'm not going to demo any of it today. But Sampler or sample will allow you to find out where time is being spent in your application, and it will give you the back traces to let you pinpoint what the call path was to that particular primitive. There's Thread Viewer, which will, if you've got a multi-threaded application, is very useful in terms of determining which threads are actually consuming the CPU. And then Shikari and Monster are two new apps, or two new utilities that have a lot of power for really drilling down and finding out what you're doing to the hardware, right? So this basically gives you full access to all the performance registers, either on an individual application basis or on a system-wide basis. But if you want to find out, or if you care what your cache hit rate is, or how many branches per second that you're executing, or on and on and on, those tools can really give you that view. Okay, for memory footprint, again, top. Just the basic default top will give you a pretty good view of what's going on in terms of or how much memory you're utilizing. Top -W gives you a lot more detail and also will provide you with a kind of running delta of what's happened since you launched top. So if you run it that way and you watch it over time, you can see whether or not your memory footprint is actually growing, and it'll detail that for you. So that's a pretty good one to run longer term. Like if you had an automated test suite, for instance, and you fired that up, I would fire up top -W along with it, let the automated test suite run for however many hours or days that you run it, and then take a look at kind of, how much, did you grow in terms of your memory consumption. Leaks. Okay, so again, after you've been running for a while, run leaks, right? Sometimes the leaks are small enough that you may not really notice them, but if they're, like as we talked about earlier, if they're there, they do add up over time. So you want to keep, kind of on top of that. Don't let it go to the last minute. And then for analysis, we have heap, which will tell you where things are, I guess, organized, where your mallocs are sitting. Malloc debug and object alloc, which is more for our Objective-C friends, I think. File system I/O monitoring. Top -D is good, again, that just gives you a good indication whether or not there's any file I/O going on at all, right? If you see file I/O going on to the disks or through the network, top will show you either. Then FS usage is a good tool for monitoring and getting a better view as to what's going on. If you've used FS usage before, we've added a couple of new things to it for Jaguar. It now actually reports any physical I/Os that are actually occurring, and also the physical block address on the disk and how much I/O actually occurred. So you can really get a feel for how random the performance of the disk really is in terms of the I/Os that you're issuing, where they're actually being pulled from the disk. And it also breaks that up into plain data versus metadata versus VM operations. So it gives you a pretty clear picture of what you're doing to the disk. Sampler has a nice feature in it that you can basically tell it to sit on any I/O operation. So you just kind of click a box, say, I want to know anytime an I/O operation is called, please record the callback stack for me so I can find out, how I got to that point. That's a very powerful way to look, to be able to track where all the I/O is coming from, because sometimes you don't issue it directly, right? It's some API that you're calling, that ends up being a fairly expensive operation in terms of file system I/O. So this would allow you to see that API, maybe you don't want to do that API in your polling loop. So, in closing, applications that perform efficiently should be your goal. We want we want all those great features. We want your apps to perform well, but we want them to perform efficiently because that makes our customers happy, right? That makes the whole system feel better, and it makes, quite frankly, as we said earlier, not in isolation. So all the apps running on the system, they're all affecting each other. So, it's to your benefit to make them perform efficiently. Memory footprint is really the enemy. I mean, if I had to pick out one thing, right, for us to focus on the next year, it would be going after reducing our memory appetite. If we could cut the amount of memory that we, as a community, so both the applications and the system, frameworks, kernel, if we could cut it in half, right, the system performance would be pretty outstanding. It would make a huge difference. The hardest part is getting started, just like a diet, right? But once you get started, we have lots of great tools available for you, and I really didn't do them justice. Like I said, I really hope you went to the 905 session. There are a lot of great tools available to help you, in this endeavor. But just like a diet, once you've met the goal, you need to think about a maintenance program, right? Again, this is an ongoing process, so you need to get this kind of built into your process of development where, as you're developing, you're monitoring these efficiencies, right? Making sure that you're not slipping and you're adding a feature and, geez, my memory usage just doubled. Well, maybe that's what it will take, right? Maybe that's what that feature requires, but at least make it a conscious decision, right, that you've just increased your memory footprint by that amount, right? It was necessary, not it just happened accidentally. Customers will definitely notice. They are going to notice that, applications, that this set of applications, when they leave them running in the background, sitting down in the dock, have no impact on the system performance. They're going to notice that other applications that are running in the background and aren't doing anything visibly, useful to them, to the customer, are causing the system to behave badly. They're going to notice if they don't have that application running, the overall system performs better. So there is a clear reason why you want to be efficient, right? Customers will tend to pick efficient apps over time. So I think Godfrey wants to come up and do one last little spiel.
First, I want to thank Joe for an excellent presentation. I hope you got a lot out of that. Some references. The Mac OS X System Overview book is always a useful reference for understanding the system architecture and how and where to get things done. Mac OS X Performance talks a lot about the same principles that Joe's been talking about, and they're available both on your disk in PDF form or as print on demand through the developer website. We have our tools page on Apple Developer Connection, where we talk about all of our performance tools and performance tools available from the third-party world. A roadmap for today. Okay, in this session, we've drilled rather deeply into principles of developing for performance. In the next session in the tools track, we're going to talk about the compilers. And a good way of getting good performance out of your applications is to understand your compilation environment, understand exactly what the compiler is doing, and where we're going with compilers. That is in room J, immediately following this session. This afternoon, we have both the Development Tools Feedback Forum in room J1 and session 908, which is not listed on this slide for reasons beyond my control. Session 908 talks about getting the most out of Project Builder to utilize the best of the build system. And again, the last session of the day, debugging in Mac OS X, right in this room, 5 o'clock this evening. And with that, I'd like to invite the Q&A panel up to the stage. For contact, discussion of performance, performance tools, if you have any need to get in touch with the engineering team, our Development Tools Engineering Feedback address, macOS10-tools-feedback@group.apple.com. That's beginning to roll off my tongue lightly now. Is a useful way of contacting the entire Development Tools engineering group, and I am always available as a primary contact.